we do solid state chemistry. I started out as an organometallic chemist, so I always was interested in soluble clusters. And going both ways, we can create reactive molecules from solids, not only checking the properties, but also using the chemical reactions of solids to make soluble clusters, and the other way around, to use soluble clusters to make back solid state compounds or materials on the other way around. And for this, you need all kinds of synthetic methods. And this is something which I like to point out as a chemist always. If you look at these elements which are used for energy pathways, so these were the windmills, we have the steam engines, we have the first combustion engine cars, and now we have all those energy conversion and storage materials, and we need the whole periodic table more or less to make those smart materials. And this is only possible if we have incredible, well-refined chemical synthetic methods. Also, this will come later on, not in the talk, but in all those materials must be recycled at one point. So chemistry is the most important step inside this business. So I will start out talking about solid state compounds. These are intermetallic compounds. We use those as semiconductors, lithium ion conductors, anode materials, superconductors. These are the materials we are working on. And on the other hand, we work on soluble clusters, which is shown here on the left side. These are main group element clusters or organometallic compounds in combination with main group elements. And for this, we introduce the term intermetalloid clusters, because if they get larger, they resemble the coordination in intermetallic compounds. So going this two ways, this is chemical synthesis is involved. And as I've mentioned, so we have the solid state synthesis as well as the important to develop. I will start with one example in solid state chemistry. So I will try to use a few isolated results which we got during the last years, but I will also show you the principles which I think is important and what is the driving force actually to come up with new ideas in these fields. If you look at a very basic concept in solid state chemistry, you have salt-like compounds or salt compounds, ionic bonds like sodium chloride. Electrons are localized. We have a transfer of the electrons perfectly localized like in molecules, and the electrons are delocalized in intermetallic compounds. For example, copper and tin. Copper and tin make a close-packed structure here. In between, but the electrons are still localized. So I increase the bar here over these so-called synthetases. And here we create often small clusters, which are called polyanions on the first step. And this is something which can be used for synthesis, especially, for example, to make intermetallic compounds, which are not accessible by just melting the elements together. And especially interesting is the field here in between, when it's not clear if electrons are delocalized or localized, and nature is not discrete. Even we teach this a lot to the students, but nature is not discrete. And in these interfaces, I think nature becomes most interesting. So let us go this first step from a salt to a synthase. Also here, nature is not perfectly discrete. And I show you one example, for example, highly charged anions. And this brings me to the point of the first application field, lithium-ion battery. We know we have well-developed lithium-ion batteries, even used for cars. The same batteries we use in the laptop we use for cars. We have some safety problems which can become huge if you're in an airplane, like in a handy or a laptop. And certainly if it starts on fire, and what is burning so well is the high charge density, which is on the lithium graphite anode, and also the liquid electrolyte or the polymer electrolyte. This is some really safety problem. In order to make it more safe and also to get higher density energy that you want to volume. And note, you solid electrolytes but they have some disadvantage, they have statics, and they are have not that as a good electrochemical stability yet as the liquid electrolytes. So there are a simple idea how we think about the electrolyte works. The lithium atom has from one side to a vacant side, and we have some energy barrier to go over this. So this is the mobility, and the activation energy controls this. On the other side, and this is the conductivity for the ionic conductivity in a very simple picture, beside the activation energy, we have the number of charge carriers, which can increase this solid electrolytes. And there are many electrolytes around. Currently, mainly these phosphide or sulfur-based electrolytes are investigated, so-called thiolysicon. We have thiophosphates. We have called argyrodides. Then we have those oxide-based materials. They are more stable with respect to electrochemical stability, and those show much better conductivities. This is shown here. So liquid electrolytes come to the area 10 to the minus 2, 10 to the minus 1, or even a bit higher. And we see these complex electrolytes based on sulfur, basically, reach in the meantime this area of liquid electrolytes. Those compounds are all built of those tetrahedral units. So I draw here the actually charges. These are not the partial charges. This is always for materials chemists. They want to see a P5 plus or E4 plus. So this is a mixture of the valence description and the charges. And it's quite simple, the chemistry behind this. But we thought if you want to increase the number of mobile charge carriers, we have to increase the charge of the anion. And so we substituted sulfur in a very simple refreshment chemistry class. You can do this by phosphorus. And we go from PS4 minus or germanium S4 minus to silicon P4 8 minus, because we have one charge more. So if those compounds would exist, we would have 8 lithium atoms per tetrahedral unit. And if we substitute the central atom by aluminum, we would have even 9 atoms per anion. Certainly such anions are not soluble anymore. This is a question also, when do we call something which is salt like a salt? If we can separate the ions, we can do this generally, classically with a liquid where we separate the ions. But we can also show if we have lithium ion conductivity, then they must be regarded as a salt. Now the question is, those compounds did not exist. So we started the field maybe 3 or 4 years ago. Nothing was known of these compounds. And to show you a few principles in solid state chemistry, how we do this, this is the so-called composition diagram. We have here on the lower side, we have the increasing amount of silicon. Here we have the increasing amount of phosphorus. And we see that along this line, we have the binary compounds like SiP2. This is a hypothetical Si3P4. And here we have 100% lithium. So for example, here's a binary Li3P. This is our compound we want to make. So we draw a line along this, and then we start to synthesize the compounds with the ratios of these boundary units Li3P and Si3P4. So we do this and already starting to scale up this later on. If you want to have a material, this must be upscalable. We have ball milling, we make press this, then we temper this in ovens. And we see after ball milling, we get a powder diffractogram like this. And after annealing at a specific temperature, this is for one specific compound, we get here a single phase material, which we can investigate with respect to structure and properties. So when we did this, we found many new compounds, and this is something which is exciting. I was asked what are most exciting things to find such a simple phase diagram, such simple compounds, and nobody investigated this the last 100 years. This is fun. This is really fun. Some other groups, your end, also started maybe 3 years ago after we published the first one in the system, but we are more interested on the lithium-rich side. So we can investigate all those phase diagrams, ternary phase diagrams with elemental combinations. And I just show you 2 examples. This is the one of Tassilo Restle, the lithium-9 aluminium P4. We got a really good diffraction experiment here and good quality. So we can really see how the lithium atoms are distributed in the vacancies. Here we have split positions. And we know in the meantime that the lithium migration goes through those octahedral sites. Generally, the lithium atoms mostly are sitting in tetrahedral sites. Here, this is a case in lithium 8 tin P4. We do also neutron diffraction, and we have various methods, temperature-dependent diffraction methods, where we can then calculate the activation energy from experimental data using the right model. And we can look for those migration paths. Again, here we see a tetrahedral site, octahedral site. Now we have a huge substance class, a totally new family of lithium-ion conductors, and they are all very good conducting materials. We do here impedance spectroscopy, and we can add those compounds, and you see that this new compound family, which is like a pure compounds, this is not optimized like we see this in the sulfides. They started with PS43- here. We start already here and got already a good increase. We're not reaching yet the top of the sulfides, but these are still pristine compounds, and we look forward when we now mixing those that we hit those. Certainly we have to still investigate the electrochemical stability, and it seems that we get maybe the same range like in the sulfides. Here are the actual values. The compounds are very light, which is always important for mobile applications. But with this example, I want to finish this part on salt-like or salt compounds. And I like to continue. First of all, I like to thank those co-workers, Hubert Gasteiger, with him we started the first impedance spectroscopy, and those people do like NMR measurements and theoretical measurements. I have to excuse with my co-workers here that I could not put all the papers on it. I just put some recent papers. This is a selection which I did fast this afternoon. Mostly I do not cite the papers because this would be too many. Now we move on to the part towards the delocalized electrons. And this is a nice result, which we found accidentally in the system lithium aluminium P2. Now we have edge sharing tetrahedra, and here we have corner sharing tetrahedra. This is a sheet structure. And by accident, because we also do always band structure calculations in the groups, I always tell people, currently this is Sabine Zeitz, please do a calculation. We found that this is a direct semiconductor. They are rare. And we have this nice cooperation in-house to measurement. So this is quite new. This is an unpublished result that we can do those measurements, which verifies that we have a direct band gap conductor. And within this family now, we found already 5 or 6 new direct band gap conductors. And this should show this image. And so the lithium ions were hardly working in these compounds, but this is a bad ion conductor. And even they tried to find the way through, it did not work. And starting out down here from electromobility or battery materials, now we got a direct band gap, and we get a totally new research field in this compound family. Now I like to move on in this area between the localized and delocalized area. And this goes back to my fascinating interest in intermetallic compounds. this fantastic structure, which is a shell type structure, actually was solved by Linus Pauling in 1957. All atoms are arranged in a shell, but those atoms are all interconnected, and each atom at the surface is the center of a next coordination polyhedra. This is typical for an intermetallic compound. In contrast, we have such shell-type structures in molecular clusters, and then they are closed up by a ligand shell. And the question is, can we maybe use these intermetallic compounds and find the kind of a scissor to cut out those clusters? Can we divide individual clusters? So the way we make intermetallic compounds is that we study phase diagrams. So here we have 100% tin on the right side, we have 100% copper on the left side, and in between, this is a complex phase diagram, we see all those copper tin phases. Actually, to make a nice sounding bell, you have to go through the phase diagram in this area, which is rather complicated. Nevertheless, there are many compounds, they already have related structure, they are close packed, they are so-called Hume-Rothery phases, and you can make them easily. You take copper and tin, heat them up, for example, with the arc furnace, and you make maybe in the composition 1 to 2 some alloy. This is a mixture of structures. But then if you add as a scissor alkali metals, we found this beautiful compound which has individual large clusters in the solid. And actually what is happening here, that we have the scissor and we cut out of the Hume-Rothery phase those clusters. And those clusters are really big, and they have a shell type structure exactly like in many other intermetallic compounds. And that's the reason these are bronzes. Copper and tin compounds are bronzes, so we call this bronze matryoshka. This is a nice Bavarian variant, not a Russian variant with a beer and a pretzel. And we are then looking into this salt type compounds, because if we transfer the electron sodium plus, then this cluster is 12-fold negatively charged. This will not go into solution, but the question is if this is right to write an intermetallic compound composed of 3 metals, sodium, copper, and tin. There are no concepts, simple concepts does not work for transition metals. If this works, then we can do band structure calculation. Here, this is like a density of states. We can do molecular calculation on this hypothetical polyanion here. And we see this is a good match. And actually, this cluster has lots of degenerate orbitals. And if we look at this cluster and we look at the overall picture, how the molecular orbitals looks like, for example, the highest occupied orbital, we get an idea that down there, this is positive charged, up there, this is negatively charged. We get some changes in sign down there. And this is nothing else like a huge p orbital. Or down here, this is the molecular orbital, and this is an atomic orbital, and this is an F-type orbital, and we can assign the symmetries of those orbitals to atomic orbitals. And this is nothing else like the superatom approach, which I, in the meantime, use this example to teach in group theory. In an atom, we have this, everybody knows this, the S, P levels, and then D levels, F levels come up. These are the energy. The atoms are freely on spheres or in orbitals around a central positively charged center. In a cluster, we take all valence electrons around this positively charged center of the cluster, and we have the same thing, except with the difference that we can reach much higher degeneracies, like in an atomic, like in an atom, which stops at the F orbital level. Here we can have more electrons, and we can even have an I level, which has a degeneracy of 13 equal orbitals here at equal energy. If we apply this, and this is maybe confusing, if you join a lecture, then you will and at the end of the lecture, we can look at those molecular orbitals which we calculated, which derive from a spherical atom. And this cluster has 108 valence electrons, and exactly those fill those levels of a spherical atom. So this is something we have like a really superatom created within this intermetallic compounds. And now we can think about what is this? Is this localized or delocalized? And certainly the electron and the question is if such things can help us also further, if we are able to dissolve such clusters.
Okay, I guess we just have lost Thomas halfway through.
It seems so. I can try and tell him. Maybe he comes back in a second.
Yeah, I'm sure he tries to come back.
Oh, he's completely left the meeting. Okay. Yeah, let's give him a minute.
Yeah, we give Thomas 1 or 2 minutes, and then we'll see.
Here he is.
Hi, Thomas. Welcome back. You're muted at the moment.
Okay, I try again. I think the blinking was the problem. May I try again? Maybe you stopped me because I was at the end of the time. Is this?
No.
So can you see this again?
Yes. So we can see your slides now.
Yeah. Okay. So if we do the same thing with cobalt and tin, we can create smaller clusters, and those clusters have a charge of 5-, and those clusters are actually soluble, and we can use those now for chemical synthesis and maybe make kinetic controlled alloys out of this. So let me see if this still works now. Yeah. If we do the same, not with a Hume rotary phase on an alloy, but with a semi-metal like silicon and germanium, we can create those really fascinating small element clusters of silicon, germanium, tin, and lead. And this opens a whole new possibility in silicon chemistry and germanium chemistry. And these are the smallest the tetrahedral and the 9-atom clusters, the smallest clusters, which are made only by silicon. There's no ligand on it yet. And this brings me to this field of soluble clusters. We can create, in the case of germanium, nice 45-atom clusters of 15 tin atom. We can introduce titanium to this, and we see how those icosahedra, so we can make those endohedral filled clusters. And here in the case of titanium, you see in solution how those icosahedra start to form around the cluster. So we can really have an idea what's going on in the solution. And those clusters, I want to show just one example that we do here. Interesting chemistry with respect to zinc-zinc bonds. This is zinc 1 compound. This cluster is 4-fold negatively charged. And here we have something like a pi system, and we can add this zinc 2+ unit to the cluster. And actually the HOMO shows that we have a zinc-zinc bond. And here we follow an interesting question. Actually, is this a complex transition metal, our main group element, ligand to a transition metal, or is this zinc a part of the cluster? The electrons are certainly delocalized, and we cannot really distinguish if zinc is a coordination compound or an atom which coordinates, or this is part of the cluster. So the things are moving, the border is fluent, and this is one of the driving forces with respect to basic chemistry. On the other hand, we do like also NMR spectra and solution. We can protonate this cluster. And the nice thing is, if you look at the NMR spectra and we do the silicon enriched compound, we see that those two protons show only one signal, and we get this huge line splitting, many lines. And the only reason to explain this is that those hydrogen atoms are in contact with the 9 atoms. So we have a process that the hydrogen atoms run around the surface. And this is certainly interesting to study hydrogen terminated silicon surfaces, which is important for the whole technology in industry who is working with silicon. If we have less than 29 silicons, we see a reduced splitting because hydrogen is only coupling to 29 silicons. So this is a perfect proof that we have this compound here in solution. Now, just to mention what many people in my group are working on, we can make silyl groups to the cluster. This is the 4-atom cluster. So we make it monoanions. We can put on phosphonyl groups. So we have like, in order to get crystal structure, often those anions are not crystallizing. We see those in solution, and this is the isotope distribution of germanium, which tells us always nicely that we have exactly this 9-atom cluster in the solution. And certainly for most compounds, we do the crystal structure analysis, and this is one of the important things here to prove what is the substitution pattern of those clusters. Those clusters, they are like 3-dimensional aromatic systems. Electrons are delocalized, and we might have here find rules of substitution similar to benzene molecule. Just recently, we added also boron-anyl groups, and this opens up a very new topic. So we have here the boron-anyl group. Again, we got the crystal structure by adding copper NHC compounds. This was starting a nice cooperation in-house that some students learned, and this I like here really, that some students do a practicum in another group, and they know they're not afraid to do those compounds when they come to my group, for example. And here there's an interesting new topic that the boron-anyl has close to this cluster an empty orbital, and we have a lone pair here. We call this frustrated Lewis pair system. And we made in the first step, the LUMO is not located at the boron atom. This is not the case here. But if they have cyclohexyl groups here, then this LUMO is located at the boron atoms. And we have here a 3-dimensional framework, a small cluster where we can put in all type of functional groups which have a specific orientation to each other, and we look forward to activate small molecules, for example, as it is shown here. Two groups cannot get in contact due to their steric, so this is a frustrated pair, and we will see if we can activate in future molecules. Just a PhD student started this month on this topic. So Gregor, is there time left? I can go very fast in just showing how we use these germanium molecules?
To be absolutely honest, I'm not really sure if there are any hard time restrictions.
Oh yes.
Terence, can you please correct me on that? So
yeah,
thank you, Gregor.
The time of the meeting is supposed to finish at 5:30.
So there's a little bit of time left, Thomas. So please go ahead.
So I go.
Let's say 5 minutes, and then we have questions.
Good. Yeah, this brings me to the last point, that we make materials out of those clusters. And what we do currently with germanium, we also want to do with silicon. We make such pre-structuring by these beads, polymethyl acrylate beads. This is a self-assembling technique, which you see here on the right side. We add the cluster in solution, and this is like how it looks like. This is an increased image. Then we add our solutions with the germanium clusters. This is one of the rare anionic possibilities to have germanium in high concentration in solution. We remove the beads, and then we get what we call an inverse opal structure. And if you look at those films, they change with the orientation, the color. This is how they look like, and exactly like a natural opal, where we have those small silica beads, which make this nice color. Each crystal is structured in a different orientation. We get diffraction with light at the same way with empty spheres. Crystallographer knows it doesn't matter if you have filled spheres or empty spheres. So we get exactly the same. So this is the impulse inverse opal structure. We can even temper this. We get thin frames of crystalline germanium, and this we can use to make thin film batteries. Currently with germanium, we will have a much higher capacity of germanium anodes with lithium compared to graphite. So this is a factor of 4. In the silicon, it's a factor almost of 10. And the problem is we get a huge volume change here. So the battery does not work that long with silicon and germanium. If we start with such microporous structure, we have much better cycling stability and our first tests. So this is the model of the empty framework, looks quite promising. And now it's just the point to do this for silicon. This brings me to the end. I cannot put all co-workers here on, which are currently in my group. The Zoom screen was not big enough. And I'm certainly hoping that to group images like this a couple of years ago, this I look forward to. So finally, I really thank the group. They are really good interacting, solid state group, theory group, and solution groups, and only this interaction makes the chemistry possible. And at the end, if somebody is interested, you just wrote a few review articles in the field. And finally, I thank you for your attention. So now I'm at the end. Thank you very much.